Hello, I welcome you all to this another interesting screencast. The problem reads determine the velocity of block A if end B over the rope is pulled down with the speed of 6 meters per second. This problem is coming from the Engineering Mechanics Dynamics 14th edition by R.C. Hibbeler. So in this particular problem, we are dealing with what we are calling a dependent. This is the dependent motion of two particles. Okay. So let's look at just this part alone so that we just explain the concept. I do the section here. So we have a pulley like so. We have a pulley like so. And then we have one rope on one end and then the other rope on the other end like so. So let's call this point B. Let's call this one C. And then let's apply here velocity of, let's call this VB. So assuming the rope is inextensible, it cannot extend. So what do you think will be velocity C at the end C? What do you think will be this velocity? Of course, you expect velocity C to be equal to minus velocity B, okay, which is equal to just VB going up, right? Assuming our positive velocity is going down like so. Okay. All right. So we are assuming our reference positive is going down, right? Like so. All right. So VC will be equal to minus VB, which is equal to VB going up. All right. So magnitude. So VC will be going up as VB goes down, and the velocity is equal. So basically, this is what we intend to do in this particular problem. But of course, this is a simpler case. In our case, we have the single rope, but it goes round a number of pulleys. Right. So first step is to define the fixed reference. So let's pick this reference as our fixed reference. We pick this one as our fixed reference. This one. So we call this one as our fixed reference. So this is our fixed reference. Okay. Right. And once we've done so, then we need to define our coordinate, positive coordinate. So going down, we are going to define it as positive. All right. Right. And then what do we have? So we have on one end here we have the position coordinate SB. We have the position coordinate SB. Let's call this as SB. And then we have the other position coordinate on the other end, because we are dealing with dependent motion of two particles, so we are always interested on for a single rope we have maximum of 2 coordinates, but if you have 2 ropes then we can have 3 coordinates. In this particular case we only have 2 coordinates, displacement coordinates. So let's call this our coordinate. Again, we are referring it from our reference system, so let's call this as SA, okay, because this is our particle A. All right. And then we do have some constant values that will never change. It will never change regardless, because we are saying SA and SB, these are functions of time. All right, so they are going to be changing as time changes, right? These are variables, they are going to be changing, right? So as the rope moves, okay, we expect SA to change and SB, hence we are calling them variables, right? Okay, so let's call this one here, this one is a fixed, it's a constant, it will not change. And then we have this constant from here, this whole lot of it will not change. This is a constant, this won't change. The whole lot of this, it will be the same. As SA and SB changes, this one will remain the way it is. The length is constant. All right, up to somewhere there. And then we have this one from there to there. This is another constant. So let's label them. So let's call this as L1. Then we call this one as L2. Then we call this one as L3. Okay, right. Here we go. So once we've done this, we can now write down the equation for the total length of this particular rope. So we are saying SA plus, SA, how many are there? We can count there, 1, 2. Okay, so there is this length and there is this length. Okay, SA, there are 2 of them. There's 1, 2. Okay, so say 2 SA plus SB is just a single one. Then we have L1 plus L2 plus L3 plus just L3, and this is going to be equal to L total. So we know that L1, L2, L3 and L total are all constants. All right, so once we've done that, we can now take the time derivative of these displacements to get the velocity. The other values are constant, so they'll just give us a 0 when we take the time derivative. So say D, I copy the whole lot of this and then bring it here like so, right? Then this is equal to D LT like so, right? Then the whole lot of this, okay, with respect to dt. All right, so this side we are going to have a 2 VA then plus a 0, plus VB plus 0 plus 0 plus 0 equal to 0. Mind you, we want to find VA, so I'll say our VA therefore will be equal to, or VA therefore will be equal to VB divided by 2 minus, okay, so this is minus VB divided by 2, and our VB is already given to us. It is 6 meters per second. Therefore VA is going to be equal to minus 3 meters per second, which is also equal to just 3 meters per second, and then we can use an arrow to say it is going up. Right, so I think this is about it for this particular problem. This is about it. There we go. So this is the final solution for the velocity of block A. So I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and I'll see you in my next screencast.